In the recent years, the Internet of Things is undergoing a relentless growth, enabling a plethora of new applications around us, such as Industry 4.0, unmanned drone deliveries, virtual reality, and remote surgery. This growth has been followed by an evolution of infrastructure architectures which are becoming more and more pervasive and heterogeneous, embedding thousands of nodes along the continuum from the IoT to the cloud. Naturally, such large-scale infrastructures suffers from node failures or overloading, traffic congestion, and disconnections of their nodes. On the other hand, software applications are also becoming more complex systems, being made of hundreds of interacting microservices, which must meet their stringent end-to-end QoS requirements on latency, bandwidth, security, just to name a few. Hence, application management should continuously decide where to place services, both at first deployment of an application and every time node failures, overloading, congestions, disconnections forbid meeting application requirements as a whole. Now, the problem of placing as interacting application services onto end Cloud-IoT nodes, so to guarantee all application requirements in a context and QoS-aware manner, is MP-hard, and thus it requires exponential time, at worst case, to be solved. The key idea of continuous reasoning is to exploit compositionality to differentially analyze a large-scale system by mainly focusing on the latest changes introduced in the system and by reusing results of previously computed analysis as much as possible. This idea has shown very successful in supporting iterative software development at large-scale IT companies. Indeed, incremental static analysis enabled by continuous reasoning permit to verify properties of every code modification and to identify bugs that can lead to crashes or poor performance as soon as they're introduced in a codebase. This is precisely the case of Facebook's Infer. Inspired from continuous reasoning and from our previous work in the field of application placement and management, we aim at extending continuous reasoning capabilities in support of the management of next-gen multi-service applications to Cloud IoT infrastructures. As we will show, this permits scaling to larger problem instances by reducing the time needed to make management decisions when only part of an application is affected by infrastructure changes at runtime, and possibly it will reduce the number of actual management operations needed to reconfigure a given application deployment. We will achieve this by mainly considering migrating only those services affected by infrastructure changes and, of course, through logic programming. Starting from this idea, we propose a novel declarative methodology in its open source prototype, FogBrain, that makes informed service migration decisions when infrastructure variations prevent running applications from meeting their hardware, software, IoT, or network requirements at runtime. Our methodology shows three main elements of novelty corresponding to very desirable properties for Cloud IoT application management support. FogBrain is declarative, more concise, easier to understand, modify and maintain when compared to existing procedural solutions, and it is also characterized by a high level of flexibility and extensibility which suits the ever-changing needs of Cloud IoT scenarios. It is intrinsically explainable as it derives proofs for input user queries by relying on Prolog state-of-the-art resolution engines, and it can be easily extended to justify why a certain management decision was taken at runtime in the spirit of explainable AI. Finally, it features scalability by supporting application management at the large scale by relying on a continuous reasoning approach to reduce the size of the considered problem instance only to those application services currently in need of our attention. And last but not least, FogBrain is open source. You can find it online with live documentation.
Okay, we now see how application requirements are modeled in FogBrain. So application consists of services, and each service may have hardware requirements, software requirements, and IoT connection requirements. All these requirements are represented by a service predicate that you see here below. So we have the service with the service ID and the 3 types of requirements. Here we have a second example for service ID 2, which again has the software requirements, hardware requirements, but it doesn't have any IoT device connection requirements. We also allow for constraints on service-to-service interaction, and in particular on latency requirements and bandwidth requirements. In this example, this is the S2S predicate defining the latency and bandwidth requirements for the communication from service 1 to service 2. Constraints on service-to-service communications can be asymmetrical, as we see here, where the constraints on the communication from service 2 to service 1 may differ from the constraint from the communication from service 1 to service 2. Here we have the example on the VR application that we put in the article. So we have a VR videos that are streamed from the video storage service to the VR driver service through a scene selector service. And you see below the application predicate defining the 3 services that are forming this application. For each service, we have their software, hardware, and IoT connection requirements. And then we have the S2S predicate defining the service-to-service constraints. We now see how infrastructure capabilities are modeled by FogBrain. The infrastructure consists of many nodes. Each node has an ID, and it features hardware capabilities, software capabilities, and it may feature IoT connection capabilities. This is represented by the node predicate shown below, where we have the ID of the node and the capabilities of the node. This is, of course, repeated for each node in the infrastructure. And you see a second example here with hardware capabilities, software capabilities, but no IoT device connection capability. We also model node-to-node latency and bandwidth capabilities. So we have the link predicate that you see down there, and the link predicates models what is the latency featured and the bandwidth featured from node 1 to node 2. Node-to-node latency and bandwidth are represented in a directional way. So we have 2 different representations for the latency and bandwidth from node 1 to node 2 and from node 2 to node 1. Here we show the Cloud-IoT computing continuum infrastructure that we describe in the article, where we see that we have a cloud data center, we have an ISP data center, a cabinet server, an access point, and finally a smartphone. So thus covering a huge part of the continuum that we can have from the cloud down to the IoT. And in the gray rectangle, you see the prolog representation that we use in FogBrain, where we have the node declarations and the link declarations. So in the node declarations, we have the software, hardware, and IoT connection capabilities, and the links describe the latency and bandwidth between pairs of nodes. FogBrain implements 2 different types of reasoning. So the first one is for the first deployment, when we need to first deploy the application on the continuous infrastructure. And this is implemented with a generate and test strategy, as you see in the prolog definition below in blue. The other part of the reasoning is perhaps the more interesting part is the continuous reasoning that is implemented by FogBrain in order to implement management decisions, which means to migrate services from one node to another, as we will see. FogBrain determines the first deployment of an application over a continuous infrastructure by exploiting generate and test with backtracking. What FogBrain does is checks for each service S the software, IoT, and hardware requirements, and it checks whether these hold in order to place service S on a node N. If this holds, then it checks latency and bandwidth requirements with respect to all the other services that communicate with S and that have been already placed by FogBrain. And this is repeated until all services have been successfully placed. Thanks to the declarative nature of Prolog, the good news is that the whole placement only amounts to 43 lines of code, which actually in Prolog terms are to only 10 predicates. The other part of the reasoning implemented by FogBrain is the continuous reasoning part. FogBrain identifies the services to be migrated due to two problems that may occur. One are problems with the deployment node, which means that the node N on which service S has been deployed is not capable anymore of supporting that service. And the other type of problem are communication problems that may occur among services. This is defined by the two predicates that you see below, the on-suffering node, which relies on the definition of this node problem predicate, and on the suffering link, on-suffering link, which relies on the definition of the communication problem predicate. FogBrain provides two default definitions for what is a node problem and what is a communication problem that you see in this slide. So the definition, the default definition of node problem is when the node is overloaded, it can't satisfy the application requirements, or it is crashed altogether. The default definition of what a communication problem can be, you see it before, you see it down there in the communication problem predicate, which defines that this happens when the link is overloaded, it can't satisfy latency and or bandwidth requirements, or the link is not available altogether. Here we see FogBrain at work with our reference example. So we see that we can invoke FogBrain with the VR application in order to find a suitable placement P. And for the first deployment, FogBrain determines that the VR driver service should be placed on the access point node, the scene selector on the cabinet server, and the video storage on the cloud. And this is what we see here with the green boxes. Now, what is interesting is that at some point, the video storage service has a problem, whether it is a node problem or a communication problem. FogBrain detects that the video storage needs to be migrated, and after that it builds a partially ground query to determine the new placement for migrating only that service, as shown in the blue rectangle below. So this way FogBrain determines a new placement that, as you see in green, it detects the new placement for the problematic service.
Before going through the experimental assessment of FogBrain, let's recap with a note on complexity. As mentioned before, our problem is NP-hard, which currently translates into a worst-case exponential time complexity big O of n to the power of s, where n is the number of available infrastructure nodes and s is the overall number of application services to be placed. Now, checking a placement for node or communication problems shows quadratic time complexity in the number of application services to be placed. If only m out of s services need to migrate, continuous reasoning reduces the overall time complexity to big O of n to the power of m. Naturally, this still shows exponential time complexity, but more likely we will only have to determine one service migration due to a single node problem incurring in linear time complexity in the number of infrastructure nodes, or 2 services due to a single communication problem, incurring in worst-case quadratic complexity in the number of infrastructure nodes. Experimental results with the VR application showed before over replicas of the illustrated Cloud-IoT infrastructure, ranging from 5 to 2000 nodes, confirm the previous complexity analysis. Indeed, continuous reasoning achieves an average 5,000 times speed up with respect to finding a new placement from scratch in the case of single node failure, and 60 times speed up in the case of single link failure. Overall, FogBrain represents the core of a continuous reasoner to support Cloud IoT application management. It is declarative, explainable, and scalable, and it achieves considerable speed up with respect to non-incremental reasoning solutions. Besides, being declarative, it is concise, only 125 lines of code, and easier to understand and extend so to account for new emerging needs compared to existing procedural solutions. As future work, we plan to extend the continuous reasoning capabilities of FogBrain to also handle changes in the application topology, such as the addition or removal of services, and to support other runtime management decisions such as application scaling and service adaptation, as well as to exploit a cost model and heuristic algorithms to determine optimal eligible placements, possibly along with constraint logic programming and incremental tabling. Besides, we intend to include the possibility to obtain textual explanation on why a certain management decision was taken by FogBrain and to exploit probabilistic logic programming to simulate infrastructure variations as per historical monitored data. Last but not least, we plan to assess FogBrain over other use cases and in testbed settings over actual multi-service applications. And before concluding, just one more thing. We invite you to visit our website, where you can find an interactive quick start tutorial of FogBrain, interactive documentation for each and every predicate, the ways you can collaborate with us, and an updated list of publications.